This is the fifth part of the sixth unit, energy of phase changes. So the good thing is that you guys are already familiar with this graph. Uh, it's telling us that on the y-axis we have the temperature when we melt a solid piece of ice and evaporate it into a gas. And on the x-axis, we have the heat absorbed, or the heat that we're putting into the system in order to achieve these changes. So there are two processes that will be utilizing the heat that we're putting in the system. The first utilization is by converting that heat energy into kinetic energy, and this is how we're going to increase the kinetic energy. Let me remind you that the particles in a liquid move faster than the particles of a solid, and in order to make the particles behave as a liquid, you're going to have to make them move faster. So, since temperature is a measurement of the average kinetic energy, we can appreciate from this graph that it is going higher. So it was a negative 50, and now it's going higher at A. We keep adding the heat into the system, and at point B, which is over here, this one over here, at point B, we achieve a flat line, which is telling us that the particles, if you look at the temperature, then it's flat because we are being told that the energy is no longer being utilized to make the particles move any faster, but it is rather being utilized to overcome the intermolecular forces, or IMF. In this case, we are dealing with water, so it's hydrogen bonding. This flat line B is called the amount of heat that we're putting in here is called the heat of fusion, or the latent heat of fusion. Latent just means hidden, and we're calling it hidden because it's not it's something that is not being recorded by a thermometer. But this is not necessary for you to know why it's called latent and all of that. This is your formula that you would be using. The M just means that either you would be using the mass in grams, or the N means the number of moles. That depends how you're doing it. Okay. Now, as we keep adding energy to the system again, at point C, we can appreciate that the heat energy is again being utilized to increase the kinetic energy. And at point D, we reach the flat line again. And this flat line tells us that the energy is now being utilized to overcome the IMFs again, to break the bonds. One more thing that I want you guys to notice here is that the flat line at D is so much longer than the flat line at B. And this is because, now it should make sense to you that when a solid is melting into a liquid, the particles are still somehow in contact, right? Because in a liquid phase, the particles are sliding past one another. But in part D, we are having to put in so much energy because when a liquid turns into a gas, they are completely disconnected from another. There are no forces of attraction between them. So we are 100% overcoming this force of attraction, and that's why we see such a large flat line. And this flat line, this D, where the liquid is now evaporating, is called the heat of vaporization, and the rest of the formula is mass or number of moles. One of the key differences that you have to remember is that when we are dealing with freezing the particles, like if we were going from this side to this side, freezing is the particles give out heat because we want them to become lazier, slower. And for this reason, they release the energy that they have. And this is an exothermic change. And therefore, in a formula, we're going to be using a negative sign if we're talking about freezing. In melting, we're not going to be using the negative sign. So every time there's an exothermic change, please remember that we use a negative sign. And we would apply the same logic over here, that if it was evaporating, then we're not going to be using a negative sign because it is endothermic. But if it was undergoing condensation, we would use a negative sign because the particles are going to be releasing the energy. So let's pause this video and try to solve the topic questions in your bundle and move on to the I do, we do, you do to completely understand or practice this entire phenomena. So 6.6 is something that you are already familiar with, again, because it's just stoichiometry. What you have to know is that you may be given the heat of a chemical reaction, which will tell you the change in enthalpy or total change of energy occurring in that entire reaction. So it is a delta H, obviously, and we just write an RXN, which just means reaction. If it's an endothermic reaction, this is how we're going to write it. If it's exothermic, because the energy is deducted from the system, we just write a negative H. Or a negative H tells us that it's exothermic. So here are two reactions. First one is hydrochloric acid and sodium hydroxide, and they have given us the heat of reaction or the enthalpy of the reaction. Okay, and here we have another reaction in which there's a negative 1120 telling us that this reaction was exothermic. Okay. And just like any other stoichiometric problems, just remember that the delta H value, which is this one and this one, it corresponds with the molar coefficients for the reaction. So what I mean by this is that in this particular reaction, 1 mole of hydrochloric acid, for 1 mole of hydrochloric acid, this is the amount of energy that we'd be utilizing. So if you have the conversion rate, you should be able to solve for any problem. And looking at the second example, for every 2 moles of this reactant, this is the energy change that would be taking place. So how are you going to be given these values? Or how are you going to be adding them to your reactions? So in an exothermic process, we can treat or we can consider heat as a product, right? Because it is giving out heat. So we could just write it as part of the products in here. And notice that we would only do this when the reaction is exothermic because it is being produced. However, if the reaction is endothermic, which you would know by just looking at the heat of the reaction, like this one here, this is the amount of energy that is going into the system. So we can simply write it to the left side where we have the reactants, which just tells us that this is what we added to the system. We can add it to the equation as if it was taking part in the reaction, and this is how you would write it. Please know that these are not actual products or actual reactants, but we can just make them part of the equation this way. So the problems in your I do, we do, you do are for 6.6 are all about stoichiometry. You may be given grams. Again, you would have to simply convert to moles. Thank you.